Hello, everyone. Thank you for joining another meeting of our reading group. Today, I'm excited to welcome a very great speaker, Hervé Bredin from Pianot AI. So many of you probably know this toolkit, already worked with that. So we are very excited to have him in our reading group. As always, if you have any question, feel free to raise your hand and ask the question directly to the speaker or drop it in the chat. I think without any further ado, the stage is all yours.
Thank you, Bonnie, for the intro and for the invitation. Yeah, I'm very happy to give this talk today. So yes, please ask questions whenever you see fit. I'll stop at a few times in the presentation, but you can interrupt me during the presentation. That's perfectly fine. So yeah, I started with this fun title because I've been at least I think it's fun. Yeah, I've been working on speaker diarization for a long time, and yeah, it's kind of like a love story for me, and it was the occasion for me to make a bad pun later. You'll see in the rest of the presentation. So just a few words about me first. So I've been a tenured CNRS researcher in France since 2008. So CNRS is the French National Research Center in France. So I started working on speaker diarization back in 2012. And yeah, it's been like 10 or 12 years where I've only focused on this particular very tricky topic, speaker diarization. And yeah, that's the name why I've put the subtitles here, the piano guy, because I think my most famous achievement is actually building the open source toolkit Piano Audio, which I started working on in 2015, I think, looking at the Git commits that I have in store here. But basically, it started as a way for me to make my research reproducible. Really, that was just the point of this toolkit. Every paper, every research result that I did went into this toolkit, and it grew with me. And but apparently, it became quite popular over the years. I have some few statistics here. For instance, on the right here, I've listed a bunch of open source toolkit really focusing on speaker diarization. And yeah, the red curve is actually the GitHub star history from Pianot. So it became quite popular over the years. The other one here that is trending is actually diart. It's a streaming toolkit built on top of Pianot with a colleague of mine who I'll mention later, Juan. And for instance, also the Pianot toolkit is very popular on Hugging Face. If you sort the models filtered by the audio tag on Hugging Face, this is a screenshot from 2 days ago, I think. The 5 most popular are actually Pianot ones in terms of downloads. The first one is not really Pianot, to be completely transparent. It's just a wrapper around the WeSpeaker speaker embedding that is used in the speaker diarization pipeline of Pianot. So based on all those things, I decided 1 year ago, a bit more than 1 year ago now, to create a company, Pianot AI, which I co-founded with Vincent, who's I think is attending the meeting here today. And I'm officially on leave from CNRS since March 1st. So it's been 2 months and a half where I'm focusing entirely on Pianot AI, the company. So let me start talking about speaker diarization. So what is speaker diarization? And first, I'll say what speaker diarization is not. Speaker recognition is an umbrella term that covers a bunch of different tasks. Like we can start by, I think, the simplest one, which is speaker verification. So speaker verification consists in answering the question, is this speaker A given a recording of the voice of one speaker? So I like to classify those tasks into several categories. So it's a supervised task in the sense that we need some kind of training data for speaker A to actually recognize the speaker later. It's utterance-wise in the sense that we only provide an answer for the whole utterance, and it's a binary classification task because the answer is either yes or no. an extension of speaker verification is speaker identification, where you no longer try to recognize a specific speaker, but a bunch of speakers. So the question is more like, who is this speaker given an audio recording? So you might have a bunch of enrollment in your training data set, and the answer is either A, B, or C in this example. So once again, it's a supervised classification task because you have some training data. It's once again utterance-wise, and it's a multi-class classification problem. Another way of extending speaker verification is to go towards what I call speaker tracking. Basically, the question is slightly different from the first one, and we are getting closer to speaker diarization. It's when does speaker A speak? So it's no longer an utterance-wise answer that you provide, but basically for every frame. What I call frame is basically every 20 milliseconds. We can consider that this is a frame in the audio, and you have to answer yes or no every 20 milliseconds. And now we are coming to what speaker diarization actually is. So it's usually dubbed as the who speaks when task. So it's different from the previous task that I described because it's unsupervised in the sense that we have no idea in advance of who the speakers might be in the conversation, and nor do we know their numbers. So it's really unsupervised in the sense that we might have never seen or heard the speaker during training, but still we would like to decide whether a speaker is speaking or not. So more precisely, every 20 milliseconds, for instance, once again, we answer this question, who speaks? So the point really is to gather, or let's say label, all the speech turn of the same speaker with the same tag. So in the conversation that we had with Puni at the beginning, so there were two speakers. So we first have to decide that there are two speakers, and all my speech turns should have been labeled as speaker A, for instance, and all of Puni's speech turn as speaker B. But the actual label doesn't matter. It could have been A and B or B and A. So in that sense, it's a clustering task. So that's what I try to figure here by changing the color. All of these outputs with different colors are actually the same output. So that's what makes the speaker diarization task a bit different from the other task, because the actual classes are not known in advance, and we don't really care about their actual names. So there are several, I like to classify speaker diarization into three subtasks. There's the batch speaker diarization, where you record a whole conversation between multiple speakers, and then only at the end, you answer the question, who speaks when? So that's batch. But you can also do that in real time as the conversation unfolds. So that's what we call what is called streaming speaker diarization or online speaker diarization. And there's another variant, which I call longitudinal speaker diarization. Sometimes it's called cross-show speaker diarization. Sometimes it's called speaker re-identification, where the idea is you have multiple conversations between the same set of speakers, or not necessarily the same, but across conversation, you aim at actually labeling the same speaker with the same label. And yeah, for instance, that has applications in the podcast industry, where you would like to actually tag the host for the whole series of podcasts. And what I like to insist on is that usually speaker diarization is not the final task. It's usually more like an enabling technology for other applications. And the most obvious one is really speaker attributed transcription, where you want to transcribe, let's say, a meeting, but you also want to assign each word to the right speaker. And you can really tell from the GitHub history that this is definitely the main use case, at least of the Pianot open source toolkit. When Whisper from OpenAI came out I think it was in October 2022. So Whisper is a speech-to-text open source model, for those of you who don't know, but I'm pretty sure all of you know already. You can really see that there's been a growing interest in Pianot when Whisper came out. And my explanation is that Whisper does a great job transcribing, but it does not provide the names or the labels of the speaker. So basically, people turn to Pianot to combine the two. And there are, for instance, the WhisperX toolkit that is famous for combining the two. So the usual pipeline for speaker diarization is that it comes first. You answer the question, who speaks when? And then once you've diarized the recording, you do speech transcription to get the words, and then there's a final application. For instance, in the healthcare industry, you would fill a SOAP form that is very standard in the US, where you have really after each consultation between a patient and a doctor, the doctor has to fill a form with a specific details. So it's nice for them to know whether it's the doctor or the patient that pronounce, let's say, the name of a medicine. There are a bunch of other applications for speaker diarization. It's training data sets of voice AI technology. Like, for instance, QTI Moshi voice assistant use Pianot to clean up or their training data set to train Moshi. Same for AudioBox for Meta. They both mention Pianot as a toolkit they use for training. And there are other nice applications like video translation with voice cloning. If you want, let's say, for instance, you would upload this, the YouTube recording of this video. You would record this video to YouTube and then automatically translate in French, for instance. Here I'm the only one speaking, but if it was an actual conversation, you wouldn't want to use the same voice in the translation to all speakers. So having the speaker diarization is really useful here. And there are also a bunch of other use cases like wearables where you record everything you're doing and then you can have a summary of who you met, who you said, what you said to whom, and this kind of stuff. So despite the fact that the community has been working on this problem for now more than 2 decades, it's still not a solved problem. I tried to explain what makes this problem difficult here. So there are the fact that we are dealing with spontaneous speech. So in spontaneous speech, there might be lots of overlap speech. In this example, this is a meeting in the AMI dataset here between 2 speakers. In this particular recording, the overlapping speech accounts for up to 40% of the actual speech duration in this recording. So it's first really tricky to detect that there is overlapping speech, and even more difficult to assign to the right speaker. Also in spontaneous speech, there are lots of short speech turns that you absolutely don't want to miss, like back channel, yes, and this kind of stuff. So the shortest the speech turn, the more difficult they are to assign, to detect and assign to the right speaker. And there's the usual suspect, like usually when you process a conversation, you don't know in advance who the speakers might be and also their numbers. And there might have some speakers speaking more than the others. And so that makes the whole problem very tricky to solve. So I'm going to do just 2 or 3 slides of explaining how speaker diarization has been addressed in the past and is being addressed now in the community. But don't expect this to be an exhaustive presentation. I want to spend more time on the 3 papers that I selected because after all, we are in a reading group. Historically, speaker diarization has been addressed in a multi-stage approach. So given the recording of the conversation, here it's a 200-second conversation. You start by extracting some features, usually a spectrogram, time frequency representation. Then the first step is to detect speech in this recording so that you can get rid of all the non-speech regions. And then once we've detected the speech regions, the idea is to use speaker chain detection to split long speech regions into speech turns where only one speaker is speaking, so that you start to have the kind of a structure of the conversation in this representation here. And once you have one speech turn per speaker over the course of the conversation, there's a step of clustering where basically we usually rely on what I call here speech turn representation, but in practice lately it's been speaker embeddings. So speaker embeddings, I'll talk I think a bit more later about those, but they are basically neural networks that project a speech turn into a high dimensional space where two speech turns of the same speaker are close to each other, and two speech turns from two different speakers are far apart from each other. And this way you can do some kind of clustering, so make groups of speech turns, and that's how you end up with colors in this graph. And it's been, so that was for the classical approach. And lately, I mean, it's been since 2018, 2019 that people have started working on end-to-end neural diarization. So basically, the idea is to train a neural network. Here in the presentation, it's mapped as a brain. So that takes as input the whole recording and output the speaker activation over time. So basically, we model the diarization as a sequence-to-sequence problem, where the input is the audio and the output is the speaker probability. So it can be seen as a multi-label classification task because multiple classes can be active at the same time. Here, in this example, the orange speaker and the green speaker are with very high probability, so likely to be active. But the only issue with this kind of approach is that usually we have to fix a priori the maximum number of speakers. In this example, there are 3 speakers. One of them is inactive. So the neural network is trying to output up to 3 speakers, but it only detects 2 here. So what's nice with this family of approaches is that it's overlap aware by design. It takes care of detecting and solving overlap speech detection. I think there was a hand raised. Ken, right? Yeah.
I just have a quick question on the feature extraction. Are you using Fermat regions in that process or just the standard septums?
Can you say it again? So do I use what?
For feature extraction,
yeah.
Are you consulting with Fermat regions or no? FERMET?
Sorry, the sound is not that great.
Oh, I'm sorry. Hold on.
Maybe no, but it's also my ear that aren't that great. So it's a combination of both, I think.
I think I have too much. Can you hear me better now? Or
yeah,
worse?
maybe.
Yeah, or maybe you could write it in the chat if it is easier.
Yeah, I could write it in the chat. Let me do that.
Yeah.
And I'll go back to this when I finish this part. I'll look at the question when I finish this part.
Okay.
Yeah. So I'm trying to summarize the pros and cons of both families of approaches. So the bad thing about multi-stage diarization, the first family of approach, is that if one of the stage makes mistakes, then the errors will propagate to the subsequent ones. It's also not very good at handling overlapping speech because we usually have to rely on a specific overlapping speech detection model that I didn't even mention in the slide before. And those 2 drawbacks or cons are actually solved by end-to-end speaker diarization because there's no propagation of errors if you have only one single step. And as I said earlier, the overlapping speech is really a first-class citizen of this family of approach. On the other hand, it's kind of tricky to train those hand-to-end neural model because basically a training sample is a whole conversation because the neural network really ingests the whole conversation. So it means that you have to collect lots of different conversation, while for speech to text, for instance, the unit might be considered the word. Here, it's the whole conversation. Also, as I said, usually we fix the maximum number of speakers when training those neural nets. But there are some ways of solving this issue, but still we are far from checking this red cross. And also because it usually rely on, I mean, it has to process the whole file in memory. It does not scale very well with file duration. So the idea here of this plot is just to come to the next step where we find a way. And this is one of the third trend that we see in the literature right now. And this is the one that is implemented in Pianot open source toolkit, actually. It's combining the two families of approaches. So the idea, so it's called ENDVC for end-to-end neural diarization vector clustering. So the idea is to process a long recording by chunks first. So let's say, for instance, this would be 10 seconds long chunks that you slide over the whole duration of the file. And for each chunk, we actually perform end-to-end speaker diarization, so the second family of approach. Except it's not really end-to-end in the sense that we are performing local speaker diarization. So for each of those chunks, you end up with a local speaker diarization. Now, the question is, how do we make sure that we have a consistent label over the course of the whole conversation? And to do that, we rely on speaker embeddings. So for each speaker in those local speaker diarization, we extract a speaker embedding. So this is represented here as a three-dimensional space, but basically each point here, the triangle, the circle, are vectors in a very high dimensional space where two embeddings of the same speaker are supposed to be close to each other, and two embeddings of two different speakers far from each other. And this way, we can actually apply unsupervised clustering, where we make groups of speaker embeddings. And this is our way of stitching back all those speaker diarization, local speaker diarization. And you end up with a nice and a diarization for the whole recording. And what's nice is that despite the fact that this model has a fixed maximum number of speakers, since the clustering can adapt to any number of speakers, you might end up with 10 speakers here, even though this is limited to 3 speakers here. And another thing to really understand is that since we are working with very small chunks here, let's say 10 seconds, you can't really have 20 speakers in those small chunks. So we can safely assume that the maximum number of speakers is very small. Usually, in the recent paper, people are using 3, 4, or 5 speaker max on those small chunks. And this makes the training those models much more easily than training for a whole conversation. And yes, that's basically the end of this first part. So maybe I can take the question if it's been written down. How can I find it?
Yeah, basically the question is, does feature extraction take into consideration the ferment region?
The fair what? Sorry?
Ferment. F-E-R-M-E-T. Ferment.
I think to see this written because I don't know this word in English. I'm sorry.
It is the name of a French educator who back in the, I don't know, maybe over 50 years ago, analyzed speech and broke it up into the 7 regions. It's a complicated
ferment. Okay, now I got it. No, not at all. Sorry, I was completely elsewhere. I was not expecting this question at all. So no, not at all. Really, historically, the approach was basically just spectrogram and not at all. So
right.
We say formant in French, and that's why I never heard it spoken.
Right. But I haven't seen anybody use that in voice recognition, and it seems like it would be helpful here.
It used to be useful, but now actually we are using neural networks to do this fixed extraction step, and more like black boxes that are really, really black box that makes the process easier in downstream. So the short answer is no, but yeah, there's been work on this. Looking at the time here,
There's
Okay.
one more question. Do you want to? There's
Okay.
like, could you elaborate on the new architecture? Does it replace the segmentation embedding models?
That one?
Could you elaborate on the new architecture? Does it replace the segmentation and embedding model?
Yeah, the completely new ones, yeah, it does all at once. Yeah, we don't even need a segmentation or embedding in this. The idea is really to just train one big neural network to do the whole thing. It works actually quite well for let's say two speakers conversation, but when you want it to generalize to new, I mean to more speakers, it will probably fail miserably. That's why yeah, people are trying to combine the advantages of the two approaches. Yeah, but yeah, it replaces everything. So I probably won't be able to discuss the three paper. I'm sorry, Jonas. I saw you. I think I saw you connected, but I'll suggest to Puni to invite you for a future reading group. You have lots of interesting things to say. So yeah, so here is the time for the pun. So basically, when I was invited for this reading group, I realized that. So I took a step back and realized really on what I actually worked on in for trying to solve speaker diarization, and I realized that my main interest is really in finding better loss functions or objective functions to train those models rather than trying to find new fancy architecture of the models. So yeah, that's why the papers that I selected here to discuss are actually focusing on the loss function to train those models rather than the actual architecture. So the first paper is called Power Set Multiclass Cross Entropy Loss for Neural Speaker Diarization. It's a paper with my collaborator Alexis Plaquet, who is a third-year PhD student at IRIT, my former CNRS lab in Toulouse, France. So to really for you to understand the contribution of this paper, I need to go a bit into more detail of how those end-to-end neural diarization network are trained. So basically, a conversation like this conversation between Alice, Bob, and Carol, these three speakers, is in this family of approaches is encoded like that. So it's basically one line per speaker and one column per frame. So each frame could represent 20 milliseconds of audio signal or 50 milliseconds, but that's the kind of resolution that you can expect here. So basically, speaker one would be active during, so Alice here would be active here and then completely inactive. So you get the idea. What's nice with this representation is that two speakers can be active at the same time. So basically, we're training a neural network to ingest the audio and to predict this. But in practice, it outputs logits or probabilities. And here, this is shown as with a gray level. So the darker, the more likely the speaker is to be active, and the lighter, the less likely. So then during training, so we take lots of conversation during training, and for which we have the actual labels, and we compute a binary cross-entropy loss between the two, and eventually the model will learn to perform diarization. And with this family of approach, you need, once the model is trained and to actually take the final decision, you need to actually compare those probabilities with a threshold that needs to be tuned to optimize the performance. So the higher the threshold, the less likely the speakers will be activated, and vice versa. And another issue with training models for speaker diarization is invariance to permutation. Let's say that the neural network would output this prediction. You'd say, looking at the speaker one, that it's completely wrong, right? It completely got it wrong. It only got the red one right. But it's because for speaker diarization, as I said earlier, we don't actually care about the actual label. It's okay to completely switch speaker one and speaker two, and this would still be correct. So this is what we call permutation invariant training. So it's okay for the model to not know on which line to put which speaker, because if Alice, for instance, was speaking with Dan and Fred in another conversation, there's no reason that Alice would end up in the first line either. So to train those models, actually, we need an extra step of trying all the possible permutation, speaker permutation of the output, and computing the binary cross entropy between the target and the permutation of the prediction, and then select the minimum of those loss. And this is how, this is why it's one of the reasons why training neural diarization problem is difficult, this invariance to permutation. And so the proposal of Alexis Plaquet in his paper about is to change the way the problem is set up. So instead of encoding the conversation in like that, we use power set multi-class encoding. So the idea is to have one class per subset of those speakers. So there's one class for when no speaker is active at all, one class for each speaker active on its own, and one class for each pair of speakers. And this way, and also there should be also one class where all three speakers are active, but in practice, this rarely happens in any conversation, or at least in very few cases. So we usually get rid of all those extra classes. So what's nice is that by switching from here to here is that we turn the problem into a regular multi-class classification problem. So with mutually exclusive classes, there can't be two classes active at the same time. If you want speaker 2 or speaker 3 to be active, S1 and S2 this class should be activated and not those two. While in the multi-label encoding modeling, you would have to activate those two. So this has a further advantage, is that instead of thresholding here to decide whether the probability is higher than the threshold or not, here you don't even need to use a threshold. You can simply find the argmax of all the classes. So basically, which class has the highest probability? And if it happens that this is this class, then you know that S1 and S2 are active at this particular frame. Yeah. So going to the result, I mean, there are much more results in the paper. I encourage you to read it if you're interested, but I'm focusing on this particular evaluation. So we train the same model, so the same architecture twice, one with the multi-label encoding formulation, and the one with the proposed one power set multi-class encoding. So DIARD is actually a quite famous benchmark in the community. It's made of 11 sub-data sets with very different application domains. So for instance, that one is conversations between friends in restaurants, very noisy, lots of cutlery noise, babble noise in the background, while at the very far right here, it's just audiobooks with one single speaker where diarization doesn't even make sense here. In the middle, there's conversational telephone speech between two speakers, for instance, or here web videos, so videos in the wild taken from, I don't know if it's YouTube or something else. And so this graph shows the diarization error rate. So the lower, the better. Diarization error rate is a combination of three types of errors, what we call false alarms. So false alarms are when the model says that they are speech when in fact it should be silence. Misdetection is the other way around, when the model says that there's no speech while in fact there's speech, but also it includes missed overlapping speech. So if there are two speakers in the conversation here and the model only detects one, it's also in the misdetection. And speaker confusion is whether all the speech turns that are incorrectly classified, incorrectly assigned to the speaker. And so we really see the effect of the power set multi-class encoding thing on, in particular, the misdetection. So if you have a closer look at so overall it improves every time. So it's always the first two bars here, except for restaurant, but that's the exception that confirms the rule. Power set is always better than multi-label, and one reason is that it's much better at detecting overlapping speech. You can see from this hatched overlapping speech overlay on top of this misdetection here that going from here to here, we detect much more overlapping speech, and we also correctly assign to the right speaker. It's almost everywhere like that. For instance, on conversational telephone speech, while the multi-label would miss all the overlapping speech, here we miss only half of it. And that makes sense because actually in the proposed approach, we have dedicated classes for overlapping speech detection. So that's the reason, I guess, why it performs better. Is there any question on this particular paper, the previous one? No? I can't see the chat, so let me know if...
Yeah, I will check the chat and I will let you know if there's any
I have a
question.
question. In the multi-class, you still need to account for permutations, right?
Yes, exactly. Yeah, so yeah, it does not solve the this problem. This is something that I forgot to say, but yes, we still have to do this minimum, except it's minimum on it's cross entropy here, but yeah, it doesn't solve the permutation problem. There have been people trying to solve the permutation problem by forcing the model to output the speaker in chronological order. Let's say the first speaker speaking would always end up on the first line or the second line. There's a paper by NVIDIA called SourceFormer lately, I think, but they still eventually rely also on this classical loss. It's just a combination of both. So on its own, it doesn't really, apparently doesn't solve the problem of permutation invariance.
Okay, there's also one more question in the chat. Do you really need to evaluate VAD and a speaker diarization together? And the explanation is because the way I see it, really the third type error is really related to a speaker diarization.
Okay, so the question is about whether we should give maybe more weights to speaker confusion rather than the two. So yes, that's a good point, except that they are usually related. In particular, the misdetection and the speaker confusion goes together. So it's very easy to have a very low speaker confusion if you miss all the speech, because you can't confuse speakers, because you don't that's in the way the DRI is computed. It's only the speaker confusion term is only computed on the regions where both the prediction and the reference says that there's speech. And if you miss all the speech, then the speaker confusion goes to 0. So it's really important to have all those terms into account in the metric. There are variants of this metric, like the Jacquard error rate, for instance, which gives a bit more weight to speaker confusion, in the sense that it diarization error rate gives more weight to the most talkative speakers. So that's an issue, because, for instance, if we have this conversation between right now, this recording, I talked most of the time, and some of you talked for a little bit. And if I were to just classify the whole speech as mine, then the DER would be very small, because I spoke 95% of the time, but still have a very low error rate, even though I completely missed you. So a Jacquard error rate is a way of weighting all the speakers in the same way. This way, even if I speak 95% of the time, you would still have the same weight as me in this metric. So that's another way of focusing on speaker confusion.
Okay, there are a couple of more questions, but maybe we could move them to the end of the meeting so you have more time to do the presentation.
Okay, thanks. Because I have only, what can you tell me a bit more? How many minutes do I have just to
It
decide?
is like 10 minutes.
12 minutes. Okay. Okay, so I'm sorry, Jonas, I'll skip your paper. So let me now talk to an extension of speaker diarization to the streaming case. So this is the work that I've done with Bilal, who was an intern with me, and we wrote this paper. So the idea is to so everything I said up to today, up to now, I mean, in the presentation, was about batch speaker diarization. When you know in advance, I mean, you have the whole conversation, the whole recording of the whole conversation before trying to process it. But there are many applications where you actually want to perform a speaker diarization in a streaming manner. You want to get feedback as soon as possible. So I need to dive a bit deeper into the architecture of the neural network that were used in the previous papers that I described. So those neural networks here are usually made of three parts. There's the feature extraction part. So it can be either raw spectrograms, not formant, but raw spectrograms or, for instance, SyncNet trainable filter banks, like some of you know here, hey Mirko. And then after this initial step of feature extraction, there is always a part of the neural network that performs sequence modeling. In my case, I've been using a lot of bidirectional LSTM, so those are recurrent neural networks that ingest the whole sequence of features in both directions, so from the past to the future and from the future to the past. And this is because we can afford to do that when we're working in an offline scenario. So if we were to adapt this architecture to the streaming or causal scenario, there are a bunch of problems to solve. Like, for instance, you can't use bidirectional LSTM. So one way in this paper that we did is we simply switched to monodirectional LSTM. And so just LSTMs that process the sequence from left to right as the conversation unfolds. And just changing this degrades the diarization error rate by a lot. And then it's not the case for all feature extraction, but some feature extraction step like SyncNet, for instance, contains instance normalization layer that also needs to have access to the whole chunk of audio. So that's also not compatible with streaming. So we had to resort to removing those normalization, and once again, a degradation of performance. We don't have this problem for the final layers in the network. Usually those final layers are the one that actually output frame by frame the speaker activation probabilities here. So that's perfectly fine. They just process the frame separately as the frame comes in. So it's okay. So the question is, how do we go back to 17.3% starting with this new architecture? We can't go back to bidirectional. We can't add back instance normalization. So the obvious idea is to allow the model for a certain latency before taking its decision. So this is what we call the look-ahead loss. So we allow, yeah, let me continue on this slide, and I'll go back exactly to this later. So the neural network, as I said, ingests the audio signal X frame by frame. So each frame is called XT, and predicts one after the other its decision, right? And the prediction after the model ingests XT, it will predict what I'll call Y hat T. Here, it's the prediction of the speaker activation at time T. And then we simply compute the loss function between, so frame by frame, that's the same. So we train the model like that. So the proposition of this paper here is simply to shift a bit the prediction. So let me explain. At time xt, when the neural network ingests the teeth frame, it will not predict the teeth frame, but it would predict what happened a few frames in the past. So those few frames are lambda here. So lambda is the actual latency of the neural network. So, and just like that, we allow the model to look ahead a bit more in the future before taking a decision in the past. And the rest of the process doesn't change. We can still compute the loss that it was done before. The only difference is that we can't really evaluate on the very last few frames of the chunk because there's no prediction corresponding to it here. And also, there are a few predictions at the very beginning of the chunk here that has no corresponding target just aligned with it. So that's the only difference. So basically, we don't even have to change the architecture of the neural network. We just change the way the prediction and the targets are aligned during training. But that's the only difference, and that's the beauty of it. And so yeah, once it's trained, so you can actually train this model with different latencies. So I've used, I think it's on the AMI dataset once again. We've used this model trained with various look ahead or various latency to perform voice activity detection, overlapping speech detection, or speaker chain detection. And what's nice is that obviously, as you increase the allowed latency, you get better and better results. Here, this is the F-score, so the higher, the better. And we almost reach the same accuracy as the offline network after 1 second latency, but even 250 milliseconds latency, it's already in the confidence interval. And same for overlapping speech detection, and same for speaker chain detection. Obviously, the higher the latency you allow, the better the results. And I have a quick demo here of what it looked like. I think I forgot to share to activate the audio. So let me stop the sharing and start again. Oh yes, I had. Yeah. Okay. So here it's a quick demo of what this kind of model can do. At the top, you will have the reference annotation. So it's a conversation between two speakers. Here, this is what a regular VAD would do. So Celero is one of them, one famous one. They perform VAD with 80 milliseconds latency, I think, but it can be tunable. This one is with 80 milliseconds latency. And here is what we call VAD on steroids. So basically, it's using the network that I've described earlier and stitch the prediction over time. And so it's not really speaker diarization because it doesn't go all the way down to speaker diarization. It does not include speaker embeddings like I mentioned earlier, but still you get an idea of what it can do.
Your mother would say, now pick up all your whats?
Toys.
Just toys?
Yes, sir, toys.
Did you ever hear of Play Pretty?
Play Pretties, back yonder, yes, sir.
So really pay attention to the fact that it's really good at detecting speaker change detection and also overlapping speech.
They would mention that some of them would call them toys, cool. And then some of them call them play pretties. Get your play pretties and put them up.
Is that right?
Right, yes,
they were small.
Oh, yes, sir.
Small things.
And homemade.
I see.
Yes, they'd make some of the homemade thing, man, yes, sir.
You get the idea. And below is the result you would get if you would allow batch speaker diarization. So that's the end of this discussion of on this particular paper. Is there any questions?
Yep. So I think someone asked, did it do it in real time?
Yeah,
and someone asked,
this is a recorded video, but yeah, it can be done in real time. In practice, I think this one was with 250 milliseconds latency. That one is with 80 milliseconds latency, but no, it was not real time here, but yeah, it's a recording of a real time processing.
Yes. Okay. So do you want to continue to the next paper, or we should continue the QA session?
So I think I'll just talk a bit about Piano AI and then conclude if you, yeah.
Perfect. Yeah.
Sorry, Jonas. So it's just 2 minutes. Yes, as I said at the beginning, I've co-founded Piano AI beginning of last year. So really our mission, because any startup has to have a mission, the idea is to democratize a seamless human interaction grounded in scientific excellence. And I really would like to highlight the grounded in scientific excellence. The idea really is to have a lab internally where we do fundamental research on this particular topic, but all things related to speaker. So I've mentioned already speaker diarization, speaker identification, separation, that was the point of the third paper, speaker attributed transcription, streaming speaker diarization, and also interactive speaker diarization, where we have humans and machine collaborate towards a perfect speaker diarization, for instance. And yeah, the point of this slide is really to say that we are committed to continue publishing, doing research around all those technologies, and we are growing the research team. So right now it's a very small team, but with lots of resources actually. So there's me, there's Juan Correa, the CTO, who is also the creator of the Diard toolkit that I mentioned earlier, and Antoine Laurent, who happens to be my co-author of the original speaker segmentation paper back in 2021, I think. And we have access, thanks to the CNRS and Gen C, we have access to lots of compute. So that's really great to actually train all those models that we're trying to scale with more data, larger models. And we also happen to have now lots of money because we announced our seed fund. And I just wanted to give a few results of where we are right now internally. So for those of you who know the performance of a Piano Audio open source toolkit, that's the light gray one, so diarization error rate, once again, so the lower the better. And so as I was saying, we are pushing the boundaries of this and trying to reduce those diarization error rate to eventually very low values. So it's getting better over time. We already have those great, for those of you who know Diard, for instance, we are around a bit slightly more than 15 DR on Diard and this kind of stuff. And yeah, one last point, we're also working actively on speaker attributed transcription, because we know that lots of people are using WhisperX and having problems combining diarization with transcription, and we are really working hard on solving this problem of combination, but really still focusing on speaker and not on transcription. We won't go the transcription road, but really finding ways to better attribute speakers to transcription. And yeah, that's the end of my talk. Thank you very much.
Thanks a lot. That's a really great presentation. Thanks a lot. So maybe we have like few minutes for a couple of questions. If you have any question, raise your hand or like write the question. So maybe we could start with Mirko.
All right. Thank you. Thank you for the great talk and the contribution also to open source. In that sense, we are very well aligned. But I actually want to ask you something a little bit more general. So, there is this big trend towards multimodal LLMs, right? Which are eating pretty much every speech task. They are eating maybe speech recognition, speech translation, and maybe in the future also diarization. So I'm wondering, what is your opinion on the future of this diarization, or in general, the future of speech processing tasks?
That's a tricky question. Thanks. So indeed, there are some cases where those multimodal LLMs actually can solve part of the problem. But I really think so they are great, but they probably won't solve all the niche problem, or not even niche, but some specific problems. For instance, I know that if you give recording of a meetings to Gemini, it might end up with some diarized transcription. But if you really are interested in very precise boundaries, very precise overlapping speech detection, these models, I don't know, I'm not, I can't really foresee the future, but they are definitely not trained to do this kind of stuff, right? They are more like more general than that, and so I'm not. Is it a question? Is it the question about are we should we be worried doing this kind of just speech only processing, or what did you?
Yeah, that's actually the same question I'm asking myself for speech training, right? What could be the future of this project in the light of multimodal LLMs, right? And I
Yeah.
think efficiency also can play a role, right?
Yeah, because then we focus. You sometimes you don't need the whole pipeline, right? You just need one particular aspect. Actually, I see that our technologies are quite useful for training those models. But yes, indeed, once they're trained, are we still useful? I'm really sure that yeah, we can find ways to be useful, especially for instance, I don't know. I'm thinking about the voice. Dubbing industry. Do I still share my screen or not? No.
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 No. Okay. It's yeah. Yeah. For instance, in the list of the applications that I where was it at the beginning? All the applications that it can be useful for. Yeah. For instance, you probably won't put a multimodal LLM in live logging wearables and this kind of stuff. For
Yeah.
a video translation, you really need very precise timestamps, right? Because then you need to align yeah the voices, the lips, and everything. So yeah, there are many applications, and I'm
Yeah.
sure if we can.
Yeah, I agree. Actually, I agree. Thank you, Hervé.
Okay. So maybe next, Yoad, sorry if I pronounce your name not correctly. Do you want to just ask your question?
Yeah. I wonder, do you have any notion of multilingual problems? So, like, speaker diarization is orthogonal to languages, you feel?
Yeah, yeah, definitely. Really, I mean, it's language agnostic. Really, language is really not an issue. The main issue is more like for any machine learning task. It's more like a domain mismatch. If you happen to have trained your model in a very clean environment and you apply it in a classroom, it would fail miserably without fine tuning to the classroom environment. But for language, since it's really relying on, as you said, orthogonal representation to the actual words that are spoken, it's really not an issue. I have lots of examples now that I'm talking to customers since I'm now in the company. I realized that, for instance, our speaker diarization model have no Greek language at all in the training set. And we have a very happy Greek customer transcribing Greek conversation. So yeah, it's really not an issue.
Thank you very much.
Okay. Ken, do you want to go ahead?
So very quickly, what is the difference in performance given a batch file versus streaming? At first, I thought it would be significant, but then when I saw what you did with the look-aheads with the LSTMs, I'm thinking it's going to be very similar. So are we talking about a big difference between 20%, or is that pretty much going to be the attribute?
So really it depends on the allowed latency. But so for very extremely low latency, like I'm talking 10 milliseconds, even VAD might be tricky. So, but for in this example here, the latency is 200 milliseconds. So in terms of, or 250, I think, in terms of segmentation, so overlapping speech detection, VAD, speaker chain detection, you see it's on par with the offline counterpart. It's really on the speaker identification part, so the speaker confusion part that it might become trickier as you have to not only reassign speech tone to previous speakers, but also detect whether a new speaker who never spoke before, you need to create a new centroid, whatever your clustering algorithm is. But there's basically, yeah, the difference comes mostly from the speaker confusion part, where you have to have some you know, guardrails to avoid creating too many speakers and yeah.
But are you saying that there's no difference in performance given batch versus streaming?
In terms of false alarm and misdetection, in terms of speaker confusion, there is.
And do you know what that percentage is?
It really depends on the latency.
Okay, that's what you were getting at, is that depending upon the latency configuration, that's going to affect it more.
Yeah,
yeah.
exactly.
I just wanted to say thank you very much. I think this was a great presentation, very, very helpful. I'm very, very happy you contribute to the open source community. I used to work for a company that did a voice assistant in the open source community, a company called Mycroft AI. Right now, we're doing my use case, just to share, is that I work for a movie production studio. We do user-generated content. We may ask a couple to tell us about their, the proposal to a wedding for a love story. And then we need to be able to determine which of the two is responding. So that is my use case, and it's completely batch, which is why I asked whether or not it mattered if I give you the entire video versus or the entire audio versus just streaming. But again, thank you very, very much. Excellent presentation. Really appreciate it.
Thank you for the feedback. Thanks.
Okay, we have a couple of more questions. I don't know if you have time to address them or you.
I have.
Okay.
Yeah.
Okay, perfect. So maybe one question from the comments first. What are your views for working on the modular speaker diarization pipeline, given the advancement with the end-to-end models in speaker diarization?
So really, it's mostly the generalization aspect. So if fully end-to-end approach will not generalize well to completely different domains, while ones that are in the middle of the two, multi-stage and end-to-end, will, in particular for this problem on estimating the number of speakers. If you happen to know that all the conversations that you're going to process are two-speaker conversation, yeah, then yes, it makes sense to go fully end-to-end. But if your system, now that I'm on the other side, let's say, I need to design systems that generalize very well to many different use cases. And you can't just train a model for two speakers. It will fail miserably for 10 meetings, online meetings with lots of participants. Some of them will just speak for 2 seconds. And so really, it's the question of generalization. That's why I don't go this direction.
So maybe from audience, Bucket, I'm not sure if I would pronounce your name correctly, but yeah, feel free to ask.
So I have two questions. The first would be like, what was why when diarization error rate is counted, like we divide by the total audio in the sum. So you mean if you have 3 audios, we count the diarization error rate by taking the total length of 3 audios and then dividing by the missed alarm, confusion, and that one. Why not to first like count the diarization error for the first audio and second, third separately, and then sum them up? Like, because I did fine tuning on my own, and then that actually was more robust system. Well, I wanted to know the reasoning behind why not to try to take the average of them rather than taking the sum. If I'd made it clear.
The average of those 3 errors, or the average of the files?
Average of basically the average would be like take diarization error rate for each audio separately and then sum them up, rather than take the total sum, because when the audios are long for 3 hours, diarization error rate shows very small number.
Yeah.
But in reality, it's really bad audio. Yeah.
Yeah. So I actually did not define this metric. I completely agree with you. That's the thing that the community converged to, that longer files in the benchmark weight more than shorter files in the benchmark. And I think that's related to the question of, I remember who, about why not give more importance to the speaker confusion, right? So that's how it's done in the community. So to have consistency with the rest of the papers, we usually keep doing this. But I agree that it might make sense to do the average of DR rather than this thing that we're doing, like sum of false alarm, sum of miss, sum of confusion divided by sum of total speech. Totally agree.
Second question would be like regarding the segmentation model. Will there be like addition to change the metric for the segmentation? Because when I was fine tuning it, it was hard. I created my own like the one average, but it was hard to integrate that into the segmentation model. Maybe some tool to add like custom metrics for to fine tune the segmentation. Will there be some additions just in the future in the piano?
You mean in the open source toolkit? I mean, contributions are welcome. Obviously, we want to. I really want this open source toolkit to keep living and improve. So happy to discuss this offline, maybe.
Okay, thank you very much.
Okay, and Ivan, do you want to ask your question?
Yes, okay. My question is whether speaker features are language agnostic, because in some countries many folks talk in several languages, e.g. Canada, folks can talk in both French and English, or I'm living currently in Armenia and my mates can talk at one and the same time both Armenian, French, English, or even Russian. And when weather model detects all these kinds of languages as the same person or different ones.
Yeah, so those models are actually trained to be independent of the linguistic phonetic content. So they should generalize to different languages, but in the same manner that when you speak, for instance, when I speak there might be a bit of stress in my voice, while when I speak to my kids, a bit of anger, or it depends. So this might have an impact, but it's usually marginal. So there's been some papers trying to papers and benchmark, open source benchmark, to actually evaluate this. There was this displace challenge, diarization challenge, organized a few years back, or last year maybe, no, a few years back, where there were conversation of Indian people speaking both English and Hindi and switching from the other one from the other, and I don't think the conclusion were that we were very dependent on this switch of languages. So it's actually quite robust to language change. But yeah, this probably needs much more studies, but this is usually not an issue. The neural networks for speaker embedding are trained for being robust to this kind of stuff.
Okay, thank you.
Okay.
That's promising.
Okay, thanks. Maybe the final question, Ming, do you want to ask your question?
Hello?
Yeah.
Can you hear me?
Yeah.
Okay. So yeah, hi. So I actually do audio visual speaker diarization for a purpose of video understanding. So basically, I actually still have a modular pipeline instead of end-to-end approach. And for now, I guess our biggest error sources are the very short speech utterances, like less than 1 to 2 seconds. But as you can imagine, like the short text like are hard to segment, hard to get good embedding. You almost get like noise embeddings. So sort of I'm thinking, do you think really the end-to-end model is the right approach? Is really the approach to address this, to handle these short speech utterances, maybe?
Either the end-to-end or that one. Basically, it's these approaches are really good at for the segmentation part. You can't really do better today. So I'd suggest to go the end-to-end road to detect very short speech turnaround. But like everything, if to train this model to be robust to this kind of short speech turn, you also have to have the training data with
Exactly, yeah.
utterance. But there's nothing you can't do. You can do with that data anyway. So
Yeah, so sort of
yeah.
at this point, like we do videos like say an hour. It's like there's still like 100 short sentences for me. We can't do anything about them. So what I really think now is, because we talked before that somebody has asked about using large language model. So basically, I was saying, okay, because you have these short sentences, they're usually like surrounded by very long sentences, and through your system, you probably get the long sentence diaries correctly. And then you run a large language model on the text itself, because you do have the surrounding context of text, and you have those speakers. Sort of large language model can help to infer what are the short sentences speakers are. So in that sense, you can sort of like mixing with large language model to under-text it or something like that.
So I think your question relates more to speaker attributed transcription. You're more interested with transcription and assigning the right speaker to the right words. And yeah, there are papers like there's one from Google, I think, called diarization LM, where they post-process speaker attributed, I mean, diarization and transcription to actually do what you just did, like getting short speech turns just by the context of the words to you know, to correct some small mistakes like that. Like if I ask you a question, you say yes, and I continue, and for some reason diarization misses it, then the LLM can actually kind of correct this. Yeah.
Yeah. So because like you said, really for short sentences, you don't have enough data to train a good model for those anyway. That's sort of, yeah. Okay. Thank you. Thank you for the presentation.
Thank you.
Thanks a lot. Thanks a lot for the presentation and for staying longer to address all the questions. We will put the YouTube and the slide on the website on our YouTube channel. Thank you everyone for joining. Next week, we have Yossi Adi from Hebrew University and Meta. Looking forward to meeting you all next week.